And as I told Natalie before, I'm happy to share the slides after the fact here as well. So if people have questions later and want to refer to things, please let me know. So FLAG is a fairly large project involving a bunch of different institutions, and of course, Green Bank being key amongst them. Where's my mouse? There we go. So the people working on this, I've kind of tried to catch everybody. I'm sure I've missed one or two people. Apologies to those people, whether they're here or not. It's a, broadly speaking, collaboration between, I'm going to put this in the order of sort of relative importance here, primarily between Brigham Young University, where the engineers are located, with Green Bank and NRAO. It started back before Green Bank Observatory split off. And then WVU was a late comer to this, actually, to help provide scientific guidance and software. The people I've marked in yellow on this slide were all students at the time they worked on this. At this point, the only students who are still working on this are Evan Smith, who's on the call. He's working on this part-time, and Mark Ruzandana, who's finishing up his PhD at BYU. So in terms of building instruments, I'd say this is a reasonably small team, certainly compared to other phased array feed projects in the world. Funding, the work I'm going to talk about today is mostly coming from NSF and came from an Advanced Technology Instrumentation grant that was jointly awarded to BYU, WVU, and NRAO/Green Bank Observatory. That finished in 2018. NRAO, through the Central Development Lab and Green Bank Observatory operations budgets, have contributed a large amount to that. I want to thank them as well. Before WVU got involved, there were many previous NSF grants. I don't know any of the details of that. But since 2018, since we haven't had any external funding, this has been supported sort of on an ad hoc basis through money that BYU's had from other grants that's sort of supporting work that's similar. And so it helps with that. And since I became department chair last year, I've been able to scrounge up some funds here and there to support work that Evan's been doing on this as well. And so I just want to thank Green Bank and NRAO in general for their support for this, as well as all the funding agencies who are hearing this call. So, big picture first off, what's a phased array feed? FLAG, the focal L-band array for the GBT, is a phased array feed, a PAF, which I'll call it. And in the simplest possible terms, it's a radio camera that is forming an image not like a traditional focal plane array, like the K-band focal plane array on the GBT, or the alpha multi-beam on Arecibo, or the Parkes multi-beam, or any of those where you have separate feed horns, but instead forms an image basically via interferometry. It's effectively an interferometer that you're putting at the focus of the telescope. In reality, it's a bit more complicated than that, but for our purposes, that'll do. So we basically are doing the beam forming either in hardware or software, or a combination thereof, after the data comes from the front end and goes down to the control room. Unlike a traditional feed horn array, which is basically like a digital camera. You just collect information from different positions on the sky simultaneously, and you sort of put the information in the bins that it came in. Sort of a traditional CCD array type thing. The reason we want something like this, I think, is fairly obvious. Why we want arrays, and that is it allows you to survey the sky much faster. That's for mapping neutral hydrogen around nearby galaxies, and for my own interest, doing searches for new pulsars or transient phenomena. Any other science you want to do at 20 centimeters, at least for FLAG, so radio recon line work as well, studying H1 and other galaxies. In principle, observations of OH, although FLAG doesn't reach that. The reason we're interested in a phased array feed as opposed to a traditional focal plane array is twofold. One is it's physically smaller. So on the left there, you can see the entire front end assembly for prime focus that contains FLAG. FLAG is sitting basically in that box. The receiver dipoles are sitting in that sort of wider box in the front, and they feed into the electronics in the back there. And the picture on the right there is me standing next to the L-band feed on top of the GBT, and that's just the front of the feed horn. Of course, it probably goes down another, it's all 5'7" of me, going all the way down another 5 feet below my feet there. So it's much bigger. So if you wanted to put, say, 7 beams on the sky at once, you would basically be taking over the entire focal cabin of the GBT. Whereas we can do something very similar with FLAG, just sitting at the prime focus. In addition, this is a cutaway view of FLAG without the front cover on it. You can see this is composed of 38 dipoles across there, so was it 19 dual polarization receivers there, and they're fairly tightly packed. On the left there is an old image of the Parkes multi-beam, which is 13 beams on the sky, and you can see the openings of the feed horns there, and they're very discrete there and well separated. That whole box is basically the size of a person. And so we can actually fully sample the sky because we form the beams electronically, either in hardware or software, as opposed to having a physical feed horn. We can have overlapping beams. So we can actually get a fully resolved image of the sky in a single snapshot, as opposed to having to move the telescope around. We still do move the telescope around to make our maps, but we can do it in a more efficient manner as a result. So FLAG, the focal L-band array for the GBT, and I'll say I had nothing to do with that acronym, it predates me, is the first cryogenic phased array feed. It's the first cryogenically cooled phased array feed. It consists of the front end, which is pictured here, a digital downlink that was built at the Central Development Lab, and the back end beamformer, which is the work that BYU, Green Bank, and WVU did. There are 19 dual polarization feeds here. That allows you to form basically 7 Nyquist sampled beams at L-band on the sky simultaneously. And they're, so they're overlapping beams. You get an instantaneous bandwidth of 150 megahertz in a wideband mode and 30 megahertz in sort of a spectral line fine resolution mode. And when we started this project, the goal was to speed up surveys by roughly a factor of 3 to 5. The system, the back end, basically has 3 observing modes. There's a calibration mode called CalCore. This is takes 150 megahertz bandwidth and splits it up into 303 kilohertz coarse channels. You can observe with roughly 1 second integration times there. That's what we use to derive beam weights. I'll talk about that a bit more in a second. There's a fine polyphase filter bank, the PFB core mode, that's used for spectral line observations, that takes 30 megahertz of bandwidth and splits it up into finer channels of roughly 9.5 kilohertz. We can dump at a rate of 0.5 seconds for that. And then there's the real-time beamforming mode, the RTBF, which is used for pulsars and transients. For that, we can only form 7 beams at a time. We have to derive the beam weights and load them into the system, into the hardware. That works over 150 megahertz bandwidth, 303 kilohertz frequency resolution. And the dump time there is 130 microseconds. So this is it gives you the ability to time or detect millisecond pulsars and fast radio bursts and things like that. Quick sketch of what the system diagram looks like. I'm not going to go into too many details here, but you can see there are sort of a few sections here. The part on the left, I don't know if my cursor is available here, the front end, which is mounted at prime focus, the GBT, is the cooled section. Collects, again, dual polarization, amplifies it in the cooled part of the receiver, It then gets sent over a digital downlink, digitized, it's over the digital downlink developed by Matt Morgan and company at the Central Development Lab, and comes down to the control room, where the data is sent through some Roach 2 FPGAs and then processed through some high performance computing nodes with GPUs to do the beamforming and data collection. So basically the stuff that's been done at the front end was work that was done by BYU and NRAO at the time, with a lot of help from Green Bank Observatory once the split happened, in particular Bob Simon and JD working on the water cooling system, which was necessary for cooling when the digital downlinks were installed. All of the digitizers, the fiber links to get it down, the frequency banks, polyphase filter bank for forming the fine channelization, packetization, all of that is work that was done primarily at Green Bank, with some help from BYU and CDL. And then the back end was primarily the work of BYU and WVU. And I'm gonna spend most of my time talking about back end work since that's what I'm most familiar with. But it really was a team effort here with a lot of work put in by all involved. The back end itself has 5 Roach 2 FPGA boards that take the data from these digital downlinks. The packetization is happening there. Sends it to 5 high-performance computers, each of which contain 2 GPUs for computation. The 150 megahertz of bandwidth that's come in is split between the high-performance computing nodes, and there's 100 frequency bins per HPC, each 303 kilohertz. When we do fine filter bank observations, we only take 30 megahertz, and again, divide it between all 5 machines there. When someone actually is observing with this system, the process is a little bit more involved than what we have for, say, using the regular L-band receiver, at least in the initial setup. The first thing you have to do when you turn the system on is establish a bit, byte, and potentially word lock. And basically, as the signals are coming down, they're coming down in a randomized order from the different receivers, from the different antennae on FLAG through the digital downlink, and it's using the statistics of that information to do an alignment of the most significant bit and byte. And so we want to make sure that we get things properly aligned such that we're getting the same signal from the same with the same timestamp effectively from each of the dipole antennas. This is an involved process, and there's some nice software to do that, but it's still something that's isn't quite ready for prime time general use yet. It requires a little bit of an art to that process, and that certainly caused many headaches over the commissioning period for FLAG. Once we have that established, things are pretty stable as long as we don't change anything in the observing setup. We observe a known point source calibrator. This might be a standard flux calibrator, but it could be a brighter source. It could be a Fornax-A, could be just 3C48. And we have to basically point the telescope, point FLAG, at each position that we would want to form a beam. So we can do a fairly quick calibration for the beam weights by just making 7 beams that are, say, Nyquist sampled. That observation sequence might take about 10 minutes, pointing off source and then pointing at each of the 7 beams and going on source again, or going off source again, sorry. Or we make a full map of the field of view, which takes about 40 minutes. That's just doing a series of RA long maps, say, in this CalCore mode, with regular position, off-source reference positions for calibration purposes. When you do a full map, you get a full map of the sensitivity of the telescope, which I'll show you in a bit, and full beam maps as well. But you can also place your beams wherever you would like within that field of view then. Wherever you've collected data as you're scanning the telescope, you can place the beam. So you have a lot of flexibility there, for better or worse. If you're observing in the real-time beamformer mode, you need to derive these beam weights before you can start the observations. You form the 7 beams in the hardware in those cases for pulsar observations. You can derive the beam weights in probably about 10 minutes from a 7-point calibration. So there's a little bit of overhead involved in that. But once you've done that, you're all set. If you're observing in spectral line mode, you do the beam forming offline. And so we would switch to that mode and then make our maps as we see fit. Everything is stable provided you don't change the observing frequency at all. If you change the observing frequency, bit and byte lock get lost and the beam weights are not necessarily valid anymore, with a couple of caveats to that, and I'll talk about that in just a sec. So regardless of how we form our beams, the field of view, effectively a sensitivity map of the receiver is shown here on the right. We can form 7 Nyquist sampled beams, independent beams, over a field of view of roughly 30 arc minutes. The contours in this image start at -5 dB from the peak response to -3 dB to -1 dB. So you can see that the full width half max here is a little less than 30 arc minutes, but we have good sensitivity out to about 30 arc minutes in this sort of hexagonal field of view. If we're missing individual dipoles, if an LNA is dead, or if something's wrong in the digital downlink, we might get a slightly skewed sensitivity map here, but in general, it doesn't affect the entire map. So if we lose it, missing something in, say, the upper right here, it's not going to affect our sensitivity in the lower left. So missing elements is a little bit worse than, say, having a dead LNA on a traditional feed horn array, but it's not devastating. When we form beams, we typically use a process called max signal to noise ratio. That's to get the maximum sensitivity at the peak of the beam. It doesn't provide any constraints on the beam shape. As I said, keep saying it's 7 Nyquist sampled beams we can form in the field of view. So on the left here is a series of beam maps derived from a calibration grid. The X's here mark where the 7 beams are in each field, and you can see for each of the 7 beams, starting with 0 in the middle and then going 1 through 6 around the outside, what those beam shapes are. And you can see the crosshairs are indicating the beam that's being formed. So you can see the central beam looks pretty nice there, pretty circular. The first contour down from the peak is the full width half max, if I recall right. There are some, you see some coma in the outer beams, and that's in part because we're using the outer dipoles in the array, and that there's less constraints on the beam shape. So you get some slight coma on the outside, but in general, in the peaks and portions of the beam shapes are good. I mentioned if we change the observing frequency, the beam weights don't become valid. Similarly, if we turn the receiver off and back on again, say between observing runs day to day, the beam weights become stale. And so if we use an old set of beam weights and apply it to a new set of data, this is what we get on the right. So these are using the beam weights that we derived from a previous day on the following day. And you can see the beam shapes are not horrible, but you can clearly see that they're degraded. The sensitivity of these beams is distinctly worse. You lose about half the sensitivity. Beam shape out to the full width half max is only changing by about 10%, though. I mentioned, but didn't really talk about the word lock procedure. Word lock basically allows you to have consistency day to day. So if we, as we get that process streamlined, that will be something that would allow us to derive beam weights once and use the beam weights that we derive over the course of weeks to months in principle. So we have the possibility of getting rid of this large overhead there. Sensitivity. This is information for 2 polarizations, X and YY, from 2 different observing runs in our early science and commissioning stages, over a wide frequency range here from 1 gigahertz up to 1700 megahertz. I apologize for the color scale here. It was not my choice. I stole it from Nick Pingle's paper. The green and the blue are those data sets, and then the sort of, I don't even know how to describe the solid brownish, purplish colors, are models from Anish Roshi and others, given the expected T-sys values. So you can see here that the array is optimized to have peak sensitivity around 1350 megahertz, but it has a fairly broad minimum there. The jumps and such are because we took this data over various 150 megahertz ranges and then pasted them together. So there's some loss of data in places due to RFI and just due to vagaries of the observing room. Something went a little bit flaky. To give you some reference points here, the top red dashed line is basically where the increased field of view of FLAG, if the T-sys is above that value, the increased field of view of FLAG doesn't make up for the worse system temperature in terms of surveys. So you can see, based on that, we can operate pretty efficiently from 1100 megahertz to almost 1600 megahertz, where we are doing as well or better than the single pixel existing L-band feed. What is quite remarkable and was better than we were ever expecting, was reported in a paper that Anish Roshi wrote back in 2018, is that the dashed red line at the bottom is what the T-sys over aperture efficiency value is for the feed, excuse me, for the existing L-band feed on the GBT. And so you can see that between 1300 and 1400 megahertz, we basically have the same sensitivity. This was better than expected. It means that we're getting a maximum increase in survey speeds. When comparing to the existing receiver and other systems out there, this is a plot here showing survey speed in square degrees per hour versus the resolution of various telescopes, various systems. The circled blue value there is the FLAG system. The orange upside down triangle below it is the existing L-band feed on the GBT. And this is for reaching the same sensitivity over the same area, basically, with the same frequency resolution for all of these different telescopes. So the only things that are surveying faster than FLAG are alpha on Arecibo due to the large collecting area, Alpaca, when it becomes operational in a couple years, has 40 beams as opposed to 7, so it will be surveying even faster than alpha. And then the 19-beam multi-beam on fast, again, because of the large number of beams and the excellent sensitivity of that system has the fastest survey speed. This plot is strictly speaking for spectral line work only. For FLAG, that it's doing spectral line surveys 7 times faster than the current L-band feed with Vegas. Doesn't necessarily have the same frequency resolution as Vegas, and the overall bandwidth can be wider for Vegas than for FLAG. But if you're observing H1, for instance, 30 megahertz of bandwidth is fine, and so they can be compared evenly. So FLAG can map 7 times faster, which is great. For Pulsar surveys, because FLAG has less bandwidth than is available through Vegas, but has a larger field of view, the expectations are that over the same area and in the same amount of time, FLAG should be able to detect 2 to 3 times more Pulsar. Survey speeds basically are about 3 times faster, roughly speaking. There's a lot of vagaries into that calculation. I'll refer you to a paper that I'm about to show you in a second if you want to see more details on that. So FLAG's doing some really excellent things in that regard and is quite competitive. So I want to highlight real quickly a few early science results we have. I'm not going to talk about the initial tests at the front end that came out in the Roshi et al. Paper 2018 at the bottom, but there are the 2 main observing modes, the pulsar or transient mode. The first results from that came out in Rajwade et al. 2019. And the spectral line results and some of the tests with beam weights are currently being refereed. And this is the Pingle et al. 2020 paper, where you have to respond to the referees' comments. They aren't too major, but There's nothing serious in there, but we still have to go through and make a few edits and changes. So that's why that paper hasn't been accepted yet, but it's coming very soon as we get that response done. So H1 mapping with FLAG. We've done a lot of observations. I keep going back to some of our earlier commissioning results because that's what's coming out in this particular paper. So these are channel maps. Every 5 kilometers per second, we've smoothed over a number of channels to get to 24 kilohertz resolution. And this is comparing the H1 morphology of NGC 6946, a big spiral galaxy in the northern sky that I've mapped previously, with the L-band feed. The L-band feed observations are much more sensitive than the FLAG observations. The orange contours are those old observations. The white contours are the new FLAG observations. And you can see here that the morphology of things and the grayscale, the color scale, is the FLAG data as well. You can see that the structures are pretty much the same here. The things overlap really well, which was reassuring to see. I'm going to show you some other fields here as well. On the right, we have a little galaxy group around NGC 4258, where we also have existing single L-band feed data, again in orange, and the white shows you the FLAG data. Sorry, white shows you the FLAG data, and you can see some very good overlap even at lower significance values. The contours here at the same flux level in all cases. On the left here is a map towards some of the clouds that Jay Lockman has observed towards the galactic center. Same setup here. Orange is the single pixel L-band, GBT L-band data. White is the FLAG data. And you have good agreement here. The one caveat with using FLAG is FLAG isn't capable of doing frequency switching. When you change the frequency, of course, beam weights are changing. It becomes a much more complicated system. And so this is using off-source positions on the sky here. So you can't really observe close to 0 kilometers per second and do a proper calibration. These are, I believe, the high positive value, positive velocities from the galactic center observation. But again, you're seeing the same broad features here, just in a lot less time. You can see we have good flux calibration here. This is from the 4258 data. These are for each of the 7 beams. If you make a map with each of them and compare them, you can see everything lines up really well. Beams 4 and 5 are the largest offsets, but even those aren't too far off. The trick here is making sure that you account for the differing beam areas when you're doing your conversion into flux Janskis, because each beam is slightly different, and that adds, again, an extra little challenge. Pulsar results, as I said, Kaustubh Rajwade did a 10 square degree survey with FLAG. They didn't find any pulsars or new FRBs, otherwise you would have heard about it much sooner. But that was consistent with expectations. 10 square degrees was a small patch of sky. I believe it was just off the galactic plane as well. But there were regular observations of a known pulsar, B201138. Myself not being a pulsar astronomer, I can't speak to this very much. I don't know much about this pulsar except it's bright and easy to detect. And so there are a few things that were picked up. This is an example of 100 sigma detection of a single pulse from this source. You can see a nice strong spike there. Frequency versus time, once it's been de-dispersed, you can see again a nice clean signal in the middle panel, and the dispersion measure versus time, again a nice well-behaved plot there. Similarly, Kaustubh ran this data through a standard FFA pipeline. Can't give you many details here, but you have time versus basically each scan here is a single pulse of the pulsar, so you can see over time the integral of the different pulse periods summing up at the bottom there, so you get a nice clean detection of the pulse profile. And then signal to noise versus dispersion measure and period. You can see that, again, we have a very strong detection of this particular pulsar. Still don't have any new detections of pulsars or transient events, but hopefully that will come in the future. So to kind of wrap up here, I want to highlight a few of the unique capabilities of flags. Right now, it's the most sensitive phased array in the world. And that's because it's cryogenically cooled. It's also the only one operational on a single dish telescope. There are only two others currently in use. Aperitif, which is an uncooled system in the Netherlands, is doing a large area sky survey of H1 and pulsars and transients, and ASCAP. Both of those are distinctly less sensitive and actually have slower survey speeds, but of course they're on interferometers, they can resolve things much better. One of the unique aspects of the FLAG backend is that it allows for post-observation beamforming. We save correlation matrices, which means we can choose different beam weights based on what we're trying to do. So every phased array feed in the world uses a max signal noise ratio algorithm. There are other algorithms out there that don't give you the same sensitivity, but can give you better beam shapes and may be more optimally suited for detecting pulsars or mapping large area H1. And so FLAG is not only good for science, but it's also good for testing new ways of using paths. And it's the only one that's capable of doing that. Everything else does real-time beamforming in all of their observing modes. There are two cryogenically cooled paths that are on their way, Alpaca on Arecibo, and the uncreatively named CryoPath for Parks. Both of these should be operational sometime or be commissioned sometime in 2022, so they're a couple of years away. Both of them are going to have wider field of views, or at least more elements in them. Parks will certainly have a wider field of view. Alpaca, I'm not sure quite achieves 30 arc minute field of view, but it gets up there. They're going to have better backends, so wider bandwidth, higher frequency resolution backends. And both of them expect to have fairly similar system temperatures to FLAG. So whatever happens with FLAG going forward, the current capabilities are going to be matched soon. I'll talk about future FLAG plans on the next slide, but I wanted to hit some sort of outstanding issues. So the last time we did any observations with FLAG was in the summer of 2018. There were a few challenges that were overcome that summer, in particular water cooling the front end and getting good stable results out of the back end. We definitely demonstrated that at that point. The way of configuring the back end has been streamlined since then, and we've made some great improvements actually in streamlining the data reduction so we can get results in principle quicker. The main problem is we haven't had people working very actively on this, so it's a part-time job for Evan right now. Nick Pingle's off working on ASCAP, and so has only been able to work on data part-time. So if we were to put FLAG back on the telescope, there are a few things that need to get sorted out still. Inevitably, when you thermal cycle a receiver, particularly one with lots of different channels, you have LNAs that die. Different signal paths might have problems, so it just needs to be checked out in that sense. If there are dead LNAs, I think there are a couple sitting down in Charlottesville right now that were sent down for repairs. I'm not sure if they've come back yet. That's not a showstopper by any stretch of the imagination, but it's nice to have everything working when you put it up. The digital downlink, which takes the data from the front end to the back end with the bit byte lock process, this was all, the hardware should still be working, but the software to do the bit and byte locking was stuff that was written by Luke Hawkins, who's of course no longer in Green Bank. It works, or at least it did work while he was there. We need to go through and make sure we can run it operationally. Again, don't anticipate any major road blocks there, but we just need to check it out. Right now, the biggest problem is hopefully one that we can diagnose and solve, and that is that the back-end computers, flags 1 through 5, are all being fairly flaky right now and are not staying on. They've all been shut off for a couple months as we try to figure out what's wrong with that system. We have funds to repair at least some of them, depending on the exact failure, whether it's replacing power supplies or cards, but there are things that we still need to check out there. Obviously, without a functional front end or a functional back end, we can't observe. Hopefully, none of these are long-term showstoppers, but they're all things that need to be sorted out. I just want to show you real quickly the flag data reduction GUI that Evan Smith has written. This is basically a one-stop shop. If you click that all-in-one button at the top, it will process the calibration scans, form the beams, and take the data and convert it into a format that can be processed by data reduction software in GBT-IDL. I believe he's planning on also adding a button to allow you to do that data processing in GBT-IDL from the same GUI. So this allows you to take a fairly straightforward 7-point calibration scan and do all of the spectral filling, derive the beam weights and apply them in under 30 minutes. This is a major improvement from what we had 2 years ago, and has basically been one of our largest roadblocks in getting science results out. Still doing some debugging and adding the functionality I mentioned for this. So we're making things more user-friendly. Of course, FLAG has not been fully integrated into the GBT, integrated with GBT observing software and stuff, so that it's not anywhere close to being a general use instrument, but it is at least getting, hopefully, to the point where it can become an expert user instrument. So this is all about what we've done with FLAG. What are our thoughts going forward? We've been talking about ways that we can improve FLAG and have a FLAG 2 for a couple years, submitted NSF proposals over the past few years, alas, without much success, but some of the highlighted things that we have looked to do, focusing at L-band at least, try to improve the front end such that we have a wider field of view. We can fit enough dipoles at prime focus to expand that field of view out to 48 arc minutes, which would be fantastic. We'd love to increase the frequency range we're operating at so that we can pick up OH as well as H1. If we increase the field of view, we can also have to increase the back-end capability, just form more beams on the sky, get it to 40 or more. Increasing the bandwidth so that we can observe as much of this front-end frequency range as possible. Upgrading to 440 megahertz should be fairly easy. And increasing the spectral line mode to get to 150 megahertz would be excellent as well. That would allow us to do a couple different things. One is, doesn't help maybe with H1 observations, but it would allow you to get, say, all the OH lines simultaneously. It would also allow you to get a bunch of radio recon lines simultaneously to improve your sensitivity for radio recon line work. In principle, we could also split that 150 megahertz into smaller spectral windows, or process less of that 150 megahertz and get finer velocity resolution. One of the main upgrades I would love to see is actually getting a raw voltage mode that would allow us to feed into the breakthrough listen backend, but also would be usable for VLBI work. And if we have a wider field of view on the GBT, that actually allows for improvements in calibration in VLBI work when used in concert with the VLBA. And that would allow us to improve the systemic errors that limit astrometry. That has particular benefits if we expand out to K-band. And one of the things that's been talked about in phased array feeds for many, many years, decades, I think at this point, is providing real-time RFI mitigation, putting nulls on satellites and stuff. We can do that after the fact with the current system, but it would be great to be able to deploy something that could be used in real time. And so these are all things that we're considering as we go forward, none of which of this has been funded. Any improvements to the back end could also support a future K-band focal or phased array feed as well. Finally, I'll just point out that there's a link from the Green Bank, from this Green Bank webpage to the BYU webpage that has all the FLAG observing documentation on it, basically. So you can find out more if you go to that link and then click the one link on that page. There's very little detail on this particular webpage, but it's a place you can find out more. So with that, I'll leave this up and finish talking. Thank you. If there are any questions, I'd be happy to take them as well.
I'll go first since no one else is speaking up. So thanks. Good to see some of these results. And I'm excited by some of the potential improvements. So I had a summer student that was looking at Pulsar, potential future Pulsar surveys with the GBT. And one of the things we looked at was certainly FLAG, as well as like a traditional L-band survey. And we were not getting results that was close to that kind of 2 to 3 times the improvement in survey speed as I would have expected. In fact, for like a totally equivalent amount of observing time over the same survey regions, but then just kind of integrating longer with FLAG, since you can cover it more quickly, we got pretty comparable pulsar numbers of like predicted new pulsars. So I'm wondering if you know any more details, or maybe this is more a question for Costin, about where some of those numbers came from. And there's also, it was like a little bit of, it was difficult to know exactly what parameters to use. Like for example, when we were trying to figure out like what a good system temperature number to use for the kind of wideband mode, you know, we saw 18 Kelvin quoted in some places, but that seemed to be more like the lowest point in the band, and 30 Kelvin quoted in other places, and 20 Kelvin quoted in other places. So I'm just kind of curious if you could shed any light on that as well. And, and also what might be good to use for the enhanced kind of FLAG and predicting what we might be able to get out of that.
So yeah, I mean, indeed, Kaustub is the person to talk to about that paper. I am an author on that paper, so I certainly looked at the numbers. There's a nice table in the Rajwade 2019 paper that shows the assumed values that we used. The differences in system temperature come about from a few different things. There's variations in assumed, well, the main one is the difference between quoting a straight system temperature, straight T-sys, versus a T-sys over efficiency. So I think in that particular paper, and looking at this, what is listed as a T-sys is really a T-sys over efficiency. So the system temperature itself is indeed, you know, around 18 to 20 Kelvin, but when you divide it by the aperture efficiency of the GBT, that's getting up to more like 25 or 30. But you can see the assumptions that we put in for the FLAG receiver for the calculations using the population synthesis for pulsars in the table 2 of his paper there. For a future FLAG receiver, when we first proposed to increase the field of view, we are actually going for an uncooled system using some new LNAs that were being developed. And
these are the ones Sandy Weinreb is developing.
Yeah, these are Sandy Weinreb's ones. So there would have been a small loss in system temperature of a couple Kelvin, I think was all that was being claimed to make up, that would sort of be made up for by the increased field of view and the increased bandwidth that we could get. So,
okay, thanks.
But otherwise, small changes in the grand scheme of things. Small, but maybe important ones.
Can I ask a really technical, well, not technical, but just kind of a fine question? You mentioned increasing the field of view from like 48 or from 30 to 48 arc minutes potentially with like an enhanced system. Is that still a kind of like the -5 dB point, -3 dB point?
That's roughly the -5 dB point, I think. Yeah.
Okay. Thanks.
Yep.
DJ?
Yeah, Jay.
This is Jay, yeah. Can you be more specific about what beam efficiency you are getting?
We're getting about, what is it in there? It's about 0.65. It's okay. Roughly comparable. It's not too different. There's long been the claim and the hope that phased array feeds would, because they're covering large areas of the focal plane, would get much improved aperture efficiencies because you can tune your beam weight such that you're optimizing the way you're filling, you're observing the dish, the telescope. Yeah. The problem is that works and seems to work in practice only if you have a really large array and are talking only about the central beams. And so I think the aperture efficiency, the T-cis over efficiency curve I showed you is for the central beam. It's going to be slightly worse efficiency in the outer beams because we have fewer dipoles contributing to it. But it's not dramatically worse.
Yeah, okay, thanks.
Yeah.
So what's your plan for getting it back on the telescope then? Or what is the plan, I guess, for getting it back?
That might be beyond my pay grade there, Glenn, but there have been a number of proposals submitted to use the instrument. And to be frank, our goal of submitting those was not because there was a specific call to put FLAG on the telescope, but just to make sure that people were aware that there is still interest in using that instrument and developing it. But honestly, we would have to make sure that everything's still working while this thing's been sitting in storage, make sure that we've worked out all the bugs on the back end before any time got scheduled. And then there needs to be a frank assessment at Green Bank of the necessary resources for testing and reinstalling it, which are hopefully not showstoppers, but with things being shut down and limited manpower on site, that can be, everything's harder.
Hey DJ, it's Larry.
Hey Larry.
I think I asked you this question a year ago or so. I just wondered if there was any update on it. I was curious about the beam shapes that you end up with and how they might actually vary. Because if you're trying to subtract any side lobe emission or anything like that, is that feasible yet?
So I showed, it'll take me a little bit to bring up the beam shapes, but I'll send the slides around. Our field of view isn't such that we can map all the way out to the side lobes. And so we can't really put constraints on the inner side lobes. The coma shape that I showed in those beam shapes is coming because they're missing, because we don't have enough dipoles basically covering the field of view. So the outer beams are always going to be slightly less constrained. So one of our hopes to improve beam shapes is to explore different beamforming algorithms. So right now, max SNR, max signal noise ratio beamforming, really just tries to maximize that peak sensitivity. Mm-hmm. It doesn't care what the beam shape itself is. And so you can get large side lobes out of that. It is possible to provide constraints, and so seeing what the trade-off is, if you say, I want a beam shape that has high sensitivity but is as close to Gaussian as I can get it, is doable. And it's just a question of what that actual trade-off is. I had a student working on some initial tests last fall of this, and it turns out you get a really great Gaussian beam if you get rid of all of your sensitivity. It's a really wide, flat beam, so not very useful. So you have to put in those constraints in a sensible way too.
Mm-hmm. Okay, we can talk offline about it. It's the problem I'm kind of interested in.
Hey, DJ, I don't know if you can speak to this or not, but is there any chance of, I don't know, tweaking the optics or something so that this could be installed in Gregorian focus instead of prime focus?
So the main challenge in switching where it's installed, putting it at Gregorian would be wonderful because, of course, there's more room at Gregorian. There's less competition. It seems like, it feels like every new receiver for Green Bank right now is going at prime focus. So there's a lot of competition up there. That would require redoing the front end, right? So the spacing of the dipoles is set by the F ratio of the telescope. So I don't know if it would simply be a case of spacing things out differently, or if the dipoles would have to change, and then what the overall area of an equivalent system would be. But I think it would be somewhat challenging. I think going to higher frequencies, you might have more flexibility in that regard. I mean, obviously, like KFPA is sitting at Gregorian focus. There would be added caveats, complications there because of what you're looking at in terms of spillover if you're putting a phased array feed at the Gregorian focus. And frankly, high frequency feeds haven't been used high frequency phased array feeds haven't been really fully tested in that regard. So how the atmosphere affects things. And so I don't know if there's a optimal spot to put a K-band phased array feed, but that's certainly something that should be explored. From a scheduling point of view, it's obviously better to put whatever you can at Gregorian.
Cool, thanks.
Yep.
Two little comment. That you could imagine if calibration was actually an issue, you could imagine calibrating on the moon because you can sort of take out the efficiency question, because essentially efficiency is one, looking at the moon with 9 arc-minute beam. We wrote a memo on it that I've actually seen used on the KFPA implemented, but again, you'd have to get on the telescope first. The other question actually was about the beam mapping time. What fraction of your time did you spend sort of getting the sort of the weights you use for that? Is that a big part of your observing, or is it just a short few second?
So the advantages we have, when comparing to like ASCAP, so ASCAP uses the sun to do its calibration. Aperitif is using, I think it's CAS-A for their calibration. They have to use really bright sources. And as I always say, the Green Bank telescope is really big. And so we can do calibration on pretty much any calibrator that's a few Janskys even. It's really quite nice. The time it takes us depends on two things. So a little bit in terms of the source brightness. You want as much signal noise as you can get when observing a calibrator. So if you go to a faint point source, you might want more time. If you're observing something fairly bright, a 3C48, something that's 10, 20 Janskys, it's plenty bright, you can do the calibration of 7 beams at least in 5-10 minutes. Not too bad. It's not much different than, say, doing a point focus, auto peak focus or something with the current system. The challenge is if you want to truly map out your beam weights, or not map out your beam weights, but map out your sensitivity, map out your beam shapes. If you need to know that, you need to have information at all those points. And so you have to do a full calibration grid, which would take 40 minutes. But again, if you can reestablish the word lock, session to session, in principle, you can use the old beam weights and reapply them. So when I showed the two different, the stale beam weights and or beam shapes and the up-to-date ones, those differences, the fact that we had any beam in the second case was kind of remarkable. There was no expectation that should have held. So the fact that things were stable enough in that situation was actually a good sign. And this is a problem, I should add, that other phased array feeds have too. If you do a hard reset of things at Aperitif or at ASCAP, you have to rederive your beam weights. So
the people that came to 140 foot from Lincoln Labs, they believed in calibration by tones more than they believe. Sort of their engineering approach was always to calibrate with a tone. It seems like a tone on the middle of the dish might be an easier way to do those weights. You'd have different sense. I mean, but that would require a bit of hardware. You'd have to but you wouldn't have to have a very strong tone. It could be remarkably weak.
This is something that's been discussed at Aperitif and at ASCAP as well, and something we talked about very early on in the process. And yes, it should allow you to basically maintain your beam weights and adjust the small differences day to day as well. It's a much better system, but again, it requires external hardware and properly accounting for the optics, basically. So given the timescales we had for development and the resources at hand, we decided to stick with on-sky calibration. But yeah, that type of tone system should work much better. At least once you've measured the beam weights once.
Very nice. I think all you really need is a bunch of outrigger small H1 antennas to start doing mapping and sort of sprinkled around the sites. What you really need, but
I wouldn't say no. It actually, I mean, the VLBI application is actually kind of related to that. You get some dramatic improvements if you can increase the field of view of the GBT to sort of match what the VLBA antennas get. You can start doing tens of microarc second astrometry. And so doing pulsar astrometry would be amazing. OH megamasers in principle. At K-band doing water masers, you could really dramatically improve things. And so that's kind of related to that.
yeah, because you're building a correlator sort of to do those kind of things.
Yeah. Well, as I said before, I'll share these slides with Natalie, and she can distribute them to everybody. If you're interested, or you can send me an email for that as well. If you have any questions, any further questions, I'm happy to stay online and chat some more for anyone who wants to. So,
Thanks. I gotta go.